So today I'm going to talk about the science, exploration, and logistics of traverses between the lunar South Pole and Clavius crater, which is a candidate site for an Artemis Base Camp. Next slide. So since I'll be expressing some personal opinions, I wanted to share with you on one slide some background that I have that's relevant to pressurized rover type traverses. I've done and participated in habitable rover traverses in Antarctica and quite a bit in the Arctic over the past decades. And I was also a scientist, crew member on the Lunar Electric Rover field test with Mike Gernhardt and Rob Ambrose from NASA Johnson Space Center and Desert Rats team at the Black Point Lava Flow in Arizona. We have done a range of work with Humvees, in particular in the Arctic, tracked vehicles in the Antarctic. We've also used them as mobile field labs for astrobiology, and of course, actually did the first field test of chute ports with some of our vehicles. Anyway, I just wanted to convey that I feel that it's actually a really unique experience to traverse uncharted terrain with these habitable rovers, where your rover is your only safety shelter, and so I'm really glad that we will have a pressurized rover on the moon, and that some of this experience can be put to bear. Next slide. So lessons learned. Pressurized rovers are really a precious crewed mission asset. The acceptable risks are different from that of an ordinary robotic rover. I think that they should be combined, our robotic exploration in uncrewed mode, with remote crew training. I think that crews on Earth preparing for pressurized rover drives on the moon will want to benefit from the time that we operate these pressurized rovers in uncrewed mode by having them serve as a remote crew. Scouting and reducing risk for crewed missions should be, along with science, one of the main goals of the usage of uncrewed rovers. In a nominal ConOps, I would really recommend that we eventually have dual pressurized rover traverses and operations, each rover trailering two individual LTVs or ATVs, and that when we use them in uncrewed mode, that we actually mimic the crewed operations in terms of them having basic parallel concept of operations, using large pressurized rovers to get to a regional area of interest, and then using small ATVs or LTVs for local exploration. Initially, when we will have only one pressurized rover, I think that we will be in a very high risk situation of getting the vehicle stuck or possibly losing it. So our use of the pressurized rover in single rover mode should be limited in range and scope. Finally, a robotic arm is essential for opportunistic sampling. We collected lots of samples on Apollo opportunistically, and it would be really essential to be able to collect samples along the way without going on EVA each time. So these would be IVA mode robotic arm sampling with crew and also without crew. Next slide. So this is the concept of operation. I won't dwell on it, but two pressurized rovers, the exploration rover and its LTVs, and the support rover with its LTVs. Next slide. Work with robotic arms from a pressurized rover in a simulation context is some work that we've done in the Arctic quite a bit with our Humvees. Next slide. And one interesting feature was the ability to have the robotic arm be able to reach the cockpit windshield for direct visual examination of the sample by the astronaut crew member. So hopefully you'll have an arm that is long enough to reach the windows. Of course, we'll have cameras examining the samples, but being able to look at a sample with your naked eye is actually a very valuable thing. Next slide. Now, what we really need on the moon is a base as soon as possible. A base is not something that ties you down to one site. On the contrary, it's a safe haven on your planetary surface and also a springboard for you to explore elsewhere. We have large bases and medium-sized bases in Antarctica, small bases as well. I've had experiences with all scales of bases, including the small one at the bottom, which is our base in the Arctic, where we go every summer. So a base is a very important thing, but of course, it's not the only thing. Next slide. What you want with your base next is a mobility system. So in Antarctica, we have large aircraft, small aircraft, helicopters for long range, medium range, and short hops, ground vehicles as well. Next slide. In the Arctic, we have a similar scenario around our little base camp. We use airplanes for long distance hops, helicopters for shorter hops, Humvees, which we use as pressurized rover simulators, and small ATVs for local exploration. Next slide. That's my dog, sorry. Artemis Base Camp, a few years ago, we looked into sites where we might establish an Artemis Base Camp in the South Polar region. The long and short of it is that we identified a few sites, and interestingly, the following year, NASA put out its own map of Artemis 3 landing regions, which actually matched pretty well with the sites that we had identified as reasonably good candidates for a base camp at the around the South Pole. But as it turns out, there's no single location at the lunar South Pole that would be really good to establish an exploration base. I think that we should establish a mining operation once we know where we would want, if we ever find a place to extract water economically. But until then, we should establish a base in an off-polar region. Next slide. So where would you do that? The far side should be excluded, should be kept quiet for astronomy. The near side is where you want your base. To first order, anywhere on the near side would be good. But I'm going to suggest for today that we focus on one option, which is to have it at Clavius in the southern hemisphere, right at the edge of the polar regions. So this is where you would want to set up a nice exploration base, as an example. Next slide. So Clavius is a vast impact structure dating back to the Nectarian, but it's superimposed on it are craters of a different age, of a range of ages, including Rutherford, which is Copernican in age, so dating back to the most recent 1.1 billion years. Next slide. Here's Clavius in its full glory. It's at centers at 58.4 degrees south. The diameter is 231 kilometers. It would have punched through what was at the time a very thin lithosphere in the Nectarian moon, and so therefore could really have brought up to the surface some very interesting materials from a shallow asthenosphere at the time. And then the depth from the rim to the general floor is about 3.5 kilometers. Next slide. We've published just a few weeks ago a geologic map of outstanding geologic features for lunar science and human exploration of Clavius. It includes, as you can see, some superimposed craters of all ages, but also some possible volcanic extrusions, vents, and pits, clusters of pits and caves as well in Rutherford, which is once again, an Copernican age crater. So those pits and caves are associated with its impact melt lava deposits, but also the impact ejecta deposit. And then there are some kilometer scale permanently shadowed regions actually tucked away. And in fact, Jack Schmidt and Noah Petro published a paper just a couple of years ago advocating that we use Clavius L, which you see on the far left, and its PSR as a possible training site before we go into PSRs in a big way at the South Pole. Next slide. So here are some of the caves that you can see in Rutherford that were mapped out with my student, Daniel Sykes. And then with my other student, Aaron Sampson, with whom I did the geologic map of Clavius, we also identified some interesting caves and pits outside of Rutherford on its ejecta blanket. The yellow dot with the red circle is our proposed site for the Clavius base. Next slide. It's just a notional location. So here are some examples of the pits and caves outside of Rutherford crater, inside Clavius crater, on the ejecta blanket of Rutherford. So we would be very close to these locations to explore if we were setting up a base at that little red dot. Next slide. So here's the proposed site of the base at 61 degrees south, 14.776. It's a place where you have some topography that could shield you, for example, from the exhaust blast of Starship landings, and yet have an infrastructure that would have room to grow, etc. Next slide. So if you were to do a pressurized rover in the context of a location like Clavius, one solution could be to start at Clavius, and you could, for example, see that this is a map of slopes, so you can actually access the interior Rutherford without having to exceed slopes of 20 degrees, which is the maximum allowed with the JAXA pressurized rover. But there are also easy routes from the south towards the South Pole, through the rim area of Clavius that are less than 20 degrees in slope as well. Next slide. Now, one can actually find a nice corridor all the way from Clavius to the South Pole with slopes of less than 13 degrees at the scale of the resolution of the LOLA data, which is about 100 meters in this mapping. And this is really interesting because this would be a traverse that would be about 900 kilometers in length. And from starting in Clavius and ending towards the South Pole or near the South Pole, we would experience progressively in an increasing way sort of the challenge of dodging the shadows of the moon as you get near the pole as the days go by. And so this would be a nice way of progressively managing how we can work around these transient shadowed regions that are going to be increasing as we approach the pole. Next slide. The scale of such a traverse is actually very commensurate to, for example, the annual traverse that's done from McMurdo to the South Pole to resupply the South Pole Station. That's a 1,200 to 1,500 kilometer traverse, depending on the route. Once again, we wouldn't do this on day one, but once you have established a route, then it can become used relatively quickly, and we could go from Clavius to the South Pole within a matter of a week, for example, once a route is established. Next slide. So that's it. The movie 2001: A Space Odyssey had it mostly right. A base at Clavius. Of course, they didn't know about the geologic wonders of Clavius at the time, except for, next slide, the Earth was in the wrong place. It's actually higher in your sky at Clavius. And this would be an area of interest. Once we find water at the South Pole or a monolith, that's when you set up a mining operation there. But until then, you don't want to be setting up a base at the pole. Next slide. And this is the next generation JAXA Toyota pressurized rover. Thank you.